principle of moments tells us that if a body is in equilibrium, if it's balanced and at rest, then the sum of the clockwise turning forces about a pivot must equal the sum of the anti-clockwise turning forces about the pivot. And that's the principle of moments. You need to be able to explain that principle and write the definition of the principle of moments and explain a simple experiment to illustrate it. So let's have a look at that. So first of all, here's the definition of the principle of moments. So when a body is in equilibrium, i.e. it is at rest or moving at a constant speed, and I'm just going to put here balanced because it will usually be with reference to a balanced system, then the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. And remember that a moment is the force multiplied by the perpendicular distance from the force to the pivot. Okay, so let's take a look at a simple experiment which will help you to illustrate the principle of moments. So what we're going to do is have a play with a ruler and some weights. Let's say that we've got 300 grams here. Now in weight terms, 100 grams is 1 Newton on Earth. So we know that we've got 3 newtons of weight due to this mass of 300 grams. Now we can find a position where, let's say, 200 grams would balance that 300 grams. So we could write here, find a position where the 200 grams balances the ruler. And let's say that you find that position and it is at 1, 2, 3, 4, 5, 6, 7, 8, 9 centimeters away from the pivot. The 300 grams, or the 3 newtons, is at 1, 2, 3, 4, 5, 6 centimeters. So that's 6 centimeters there. The 200 grams has a weight force of 2 newtons. So we've got 2 newtons pushing down there, which is perpendicular to the distance away of 9 centimeters. So let's test out the principle of moments, that the sum of the clockwise moments equals the sum of the anti-clockwise moments. So the clockwise moments are going this way. So we're going to cross the screen. So we've got force times distance. So that's 2 newtons multiplied by 9 centimeters. And let's look at the anti-clockwise moments. Those are going this way. And that would be force times distance, 3 newtons multiplied by 6. And lo and behold, you got 18 equals 18. So it works, and it illustrates the principle of moments. It's a good one to be able to explain if you're asked. So the units, by the way, because this is force, and it's a force of 2 newtons for this guy here, and this is centimeters, we could say that this is Newton centimeters, and this would also be Newton centimeters. It's usual to write the units of a turning force as Newton meters, but in this case we've used centimeters, so that's acceptable. Hope that makes sense. See you in the next flashcard.
Torque and couple. Objectives: to know the knowledge and understanding the concept of torque, to know the knowledge and understanding the concept of couple. Now we shall discuss about torque. Torque. Look at this example. When a toy bus is held firmly by placing a finger on its top and the horizontal force is applied at one of the ends of the toy such that the force is perpendicular to its length, it starts rotating about the fixed finger. Look at this example. Consider the door of your classroom and try to turn or rotate it by applying force at various points on the door. We find it difficult if the point of application of force is nearer to the axis of rotation or hinges, and if the force is applied exactly on the hinges, the door cannot move. Look at this example. Have you observed that? A tight wheel nut cannot be unscrewed by the bare hand, but the same can be done quite easily using a jockey rod or a spanner. These examples suggest that rotating effect is decided not only by the magnitude of applied force, but also perpendicular distance of the force. When lever arm length is doubled, it is seen that the effort of force required to turn the nut is halved. Moreover, if direction of force is reversed, the sense of rotation will also be reversed. Further analysis reveals another interesting point. If F is applied parallel to lever arm of spanner, it is observed that there is no turning effect. And if F is applied at an angle theta to lever arm, the component F sin theta alone participates in rotating the system. Hence, the rotational analog of force is moment of force. It is also referred to as torque. Torque or moment of force. Definition. It is defined as the turning effect of a force about a fixed point and is measured as the product of magnitude of force and the perpendicular distance of line of action of the force from the fixed point. Let a force F acts on a single particle at a point P in toy plane, whose position vector with respect to the origin O is r bar. The magnitude of moment of the force, or torque of the force F about the point O, is given by tau is equal to force into perpendicular distance of the force from the axis of rotation. Tau is equal to force into r perpendicular, that is, tau is equal to r cross F. From figure sin theta is equal to r perpendicular by r. That implies r perpendicular is equal to r sin theta. Therefore, tau is equal to Fr sin theta. R is magnitude of position vector. F is magnitude of the force F. Theta is the angle between R and F. Torque of the force F about a point O in vector form is given by tau is equal to R cross F. The direction of torque is perpendicular to the plane containing both R and F. Its direction can be determined by using right-hand thumb rule. Moment of force is a vector. The CGS unit of moment of force, torque, is Dian centimeter. The SI unit of moment of force, torque, is Newton meter, Nm. The dimensional formula of moment of force is ml square T inverse square. Its dimensions are the same as those of work or energy. It is, however, work. The magnitude of tau of a force F acting at a point P with respect to O depends on R, F, and theta. Note 1. For a given value of R and F, torque, tau, is maximum when theta is equal to 90 degree. tau maximum is equal to Rf. Note 2. For given value tau is 0, where theta is equal to 0 degree, that is, line of action at force passing through point O. Example 1. Torque of force F acting at point A with respect to O is given by tau is equal to Ra cross F is equal to RAF sine theta, where theta is the angle between Ra and F. 2. Torque of force F acting at a point A with respect to the B. Tau is equal to Ra minus Rb cross F is equal to Ra minus Rb. Torque on a rigid body about an axis. In case of a single particle, if a single force or number of force acting on the particle, then the torque due to determined by the formula tau is equal to R cross F net. In case of a rigid body, in a single force or number of forces acting on it at different positions, then the torque is determined by using tau is equal to R1 cross F1 plus R2 cross F2 plus so on. Therefore, tau is equal to R1 cross F1 plus R2 cross F2 plus R3 cross F3 plus so on. Or tau is equal to tau 1 plus tau 2 plus tau 3 plus so on. Note, if the force vector possesses or passes through the axis of rotation, torque produced by a force above that axis case be 0. Note, moment of force or torque which tends to produce rotation in anticlockwise direction is taken as positive, whereas the moment of force which tends to produce rotation in clockwise direction is taken as negative.